to start talking about linear regression, and some of this I think is going to be a review for most of you, but it might be in a little bit of a different format than what you're used to seeing it in. So we're going to be talking about linear regression, and in particular, we're going to be looking at this in matrix form. So the questions behind linear regression are generally, is there a relationship between a response variable and predictors? How strong is that relationship? What is the uncertainty? And how accurately can we predict a future outcome? So simple linear regression looks like this. You've got some outcome variable y, and it's equal to some intercept, beta 0, plus a slope, beta 1, times x, our predictor, plus some error, epsilon. So again, beta 0 is the intercept, beta 1 is the slope. Beta 0 and beta 1 are sometimes called coefficients or parameters, and epsilon is the error. Then we estimate this with this equation. So we estimate this with y hat equal to beta 0 hat plus beta 1 hat times x. So y hat is the prediction of y when x equals little x. And so for a given prediction value, so for our predictor value, when our predictor is little x, y hat is what we would expect y to be. So the hat here denotes that this is an estimated value. That's what the hats mean, that we're estimating this thing. So we're estimating this y value, and we're also estimating beta 0 and beta 1. And so there are some assumptions that underlie simple linear regression. And so for an observation yi, we expect that it's equal to beta 0 plus beta 1 xi plus this error epsilon I, where epsilon is distributed, normally distributed with a mean of 0 and a variance of sigma squared. And so we would have one of these for each of our observations. So for y1 all the way through yn, each one will have the same beta 0 and the same beta 1 value, but they'll have different x values, so different predictions and different error values. And they'll also, of course, have different outcome values. And so we can write this like a matrix, like this. And so instead of writing this y1 equal to these different linear equations, we can write it like this, where the vector of y, so this is a vector with n components. We've got one column and n observations, and that's going to be equal to this, this object here, this beta 0 plus beta 1 x, plus a vector of our error terms. And we can split out that linear part, so I'm going to go back and forth here just so you can see what I've done, but basically I'm pulling out this beta 0 and beta 1, and I'm multiplying that vector times this matrix. And so now this matrix in this simple linear regression form is a vector. It's basically got all ones at the beginning. So the first column is just ones, and the second column corresponds to our x values for each of these observations. So if we go back here, we can see exactly how that happened because everybody has the same intercept value, the same beta 0. So that's why we're going to be having that column of ones, and then everyone has a different x value to correspond to their beta 1. So it comes out like this. So this is the matrix form for simple linear regression. And this, we call this big X. It's usually denoted as this bold X to indicate that it's a matrix. And this is the design matrix. That's what we call it when you basically append this column of ones to our predictor values. So this is our design matrix here. What do you think the dimensions are of this design matrix? So this design matrix is going to have n by 2 dimensions because there are n observations. So from observation number 1 all the way to observation number 10, and there are 2 columns here. In simple linear regression, there are 2 columns in a design matrix because the first column is all ones and the second column contains the predictor value. So we've got a design matrix here with 2 columns, n rows. We've got a vector of parameters. This is our beta. And then we've got our error terms, our epsilons for each observation, and as well as our outcome. So what do you think the dimensions of beta are? So because this is an n by 2 matrix, and this is going to be a 2 by 1 matrix, and so that's going to allow you to multiply those together. And then, of course, you've got your vector of error terms. What do you think those dimensions are? So it's going to be just one column with n observations. And then our vector of responses, And that, again, is going to be just one column with n observations. So we can write this formally as this y equals x beta plus epsilon. So this is basically shorthand for this matrix equation here, where x is a design matrix that starts with a vector of 1s or a column of 1s, and the subsequent columns correspond to the predictor values. And in simple linear regression, it's just going to be one column of predictor values because we just have one predictor in simple linear regression. So we can write the predicted values like this. So when we're estimating this, you'll notice these are estimates because they have hats on them. And so now we've got our vector of predictors here, y hat, and that's going to be equal to x, our design matrix here, times our estimates for beta, this beta hat 0 and beta hat 1. And this epsilon is going to be equal to yi minus y hat. And so you can rewrite that as yi minus beta 0 hat plus beta 1 hat times xi. So this is the residual for observation I. And so how do we pick beta 0 and beta 1 hat? What is the thing we're minimizing? So think back to when you took your last statistics class, probably your Stat 212, I think is where you would have first learned this. But what are we trying to minimize in simple linear regression? Basically, we're trying to minimize our errors or our residual sum of squares. And so this can be written as the sum of the errors squared. So from 1 to n, we're basically trying to minimize these errors. And we can actually rewrite this with yi and xi. And so we can write this, the residual sum of squares can be written as y1 minus beta hat 1 times x1 squared plus y2 minus beta hat 0 plus, or minus beta hat 1 times x squared, all the way to yn minus beta hat 0 minus beta hat 1 xn squared. So in matrix form, we can write it like this. The sum of these residuals is going to be equal to, the sum of the squared residuals, rather, is going to be equal to this equation, where basically we're going to multiply each component. So the way that matrix multiplication works is you essentially multiply this first component by the first component here. So that's the equivalent of squaring this value. And then you add it to the square of the second component times the second component. So it ends up being the same as summing up these squared values. So we can write this as the residual transpose times the residual. And what can we replace this EI with? So it turns out that we can replace this with y minus x beta. And so we've shown that this in matrix form is what that residual is going to be equal to. And so instead of having the residual transpose times the residual, we can do y minus x beta transpose times y minus x beta. Okay, so this is the thing we're trying to minimize with respect to beta. In calculus, how do we typically minimize things? We take the derivative, and then we set it equal to 0. So in this case, because we're trying to minimize this quantity and the unknown here is beta, we're going to take the derivative with respect to beta, and then we're going to set that derivative equal to 0 or a vector of zeros, and then we're going to solve for beta. And so that's how we're going to get those beta hat estimates. So let's do that. Now first I'm going to sort of walk you through this with some matrix facts along the way. So the first matrix fact that I would like for you to remember, if you haven't recently taken a class where you worked with matrices, is that if you have a matrix C that's equal to the matrix A times the matrix B, if you take the transpose of that matrix C, then that's going to be equal to B transpose A transpose. So what I want you to do is to try it. I want you to distribute or FOIL to get rid of parentheses in this residual sum of squares equation. I'm going to give you 2 minutes to do it, and I want you to go ahead and do this in the application exercise. There are a couple of you that are in both this class and my linear models class. And this is going to be a review from what we covered in linear models a couple weeks ago. And so feel free, if you feel comfortable with the material, to skip ahead and just turn in the same application exercise. Or if you'd like another chance to practice this again, feel free to take that opportunity as well. So make sure you still turn something in, even if you're in both classes. You can turn in the application exercise from the other class if you don't want to kind of go through the motions again. Or you can kind of practice it again. I think it's always good to get practice. So what I want you to do is go ahead and distribute, get rid of the parentheses in this RSS equation. Okay, so make sure to save that output, and we're going to be adding to it in the subsequent lessons. And so keep it open so that you can keep adding to it.